Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, what we are going to do is basically apply a theorem that we've seen in exterior calculus, which is the theorem, or like the fundamental theorem of calculus in exterior calculus. And what we are going to see is basically how we can apply that to retrieve a very famous theorem of vector calculus called the Divergence Theorem. And so the goal here is to show that it's a simple application of that much more general theorem. Okay, so before starting, let's have a recap on exterior calculus. Usually people are not necessarily particularly trained in this, so I do try to make as many recaps as I can when I actually talk about exterior calculus. Here, the bottom line is that we are going to work, for example, in Rn. It's not limited to that, but here, let's work in Rn. And then we define what we call the exterior product between what we call differential forms. So differential forms are things that are going to be of the form du, and this u is a function of the variables here. Basically, that's kind of it. And we are going to see kind of how that works. But the bottom line is that if you've got such differential elements and you take the exterior products, then it has this following property. It has to be anti-symmetric. Okay, so it has to return a minus sign if you swap the differentials. And consequently, you actually get that the exterior product of a differential with itself is going to be 0. Okay. Now, when it comes to characterizing the exterior derivative, the way at least I like to do it is basically by specifying first the notion of zero forms. And zero forms are basically some scalar function. So it's a map that basically goes from Rn onto R. And so that's going to be this function f, for example. Here I put x, y, z, just in case, for example, you would be in 3D, but you can extend that in more general form otherwise. So in fact, maybe I will actually do that now. So here you're going to have, for example, x1 and then xn. And here I had written df as if you were in 3D. Okay, so df dx dx plus df dy dy plus df dz dz. That's a traditional so-called total differential of a scalar function. But you can write that in a more general form as well, as being the sum. And then that's basically I ranging from 1 to n, and then df dxi dxi. Okay, that's another way to look at it. Now, the way it works is that then we can apply that particular definition to the general case. And in the general case, you define what is called a K form, or K differential form, that I'm going to call omega, and K here has to be less than or equal to n. Okay? And what happens is that you define this omega, and the most general form you can write for omega is of that form. So you're going to have here K minus 1 wedge products or exterior products between differentials. And here you're going to have scalar functions, which are the components of that K form, and that are scalar functions. So then if you want to know what is the exterior derivative of this thing, it's easy. You just say d omega is equal to, so you still have this constraint, and then you've got here d omega, and then, yeah, so you basically take d omega and you wedge it with the rest of it, okay? That's basically how that works. In my view, this is the simplest way of looking at this exterior derivative in general. And so once we have that, then we can actually state the fundamental theorem of calculus. So if you imagine that you take a compact subset of Rn, so a compact domain of Rn that has a boundary that you denote d of omega, and then you consider a k form omega, then you can write that the integral of omega over the boundary d omega is equal to the integral of d omega over the totality of the domain itself, omega. Okay, now this is caveated by the fact that you need obviously omega and d omega to actually exist in these particular domains. So usually what that means is that if you've got poles or stuff like that, then these things are not going to work very well. Okay, so that's kind of the idea, and that's what we need to care about. And in fact, I will provide some examples in later videos in, for example, fluid dynamics, and we're going to see that things can be quite not as simple as we may think. Okay, so now what we want to do is basically we choose n is equal to 3. So traditionally, the divergence theorem is actually used in 3 dimensions, in electromagnetism, for example, in fluid dynamics as well. And so that's where we want to work here. That's not to say that we can't do something more general, but we would have to use this particular theorem to work this out. Okay? So what we want to do here is basically we choose n is equal to 3 and a form that we are going to write like this. So omega tilde xy dx dy plus omega tilde zx dz wedge dx plus omega tilde yz dy dz. Okay. Now I don't necessarily write it exactly in that form, and we are going to see why in a moment. So this could be used fine, but the reason why I'm not doing that is because just now I'm going to try to relate this omega tilde to some other kind of omegas, so some additional notation, if you will, that we are going to find more intuitive. Okay, so so basically what I'm going to do here is try to look at what the Hodge dual of this guy actually is. And so here I'm going to look at the Hodge dual. And don't worry, I'm going to remind you what that is. So Hodge dual, just to remember, it basically take, so that's a star operator. And the star operator is actually so Hodge dual star is basically taking a form omega in lambda k, and it's basically returning another form, but that is in lambda n minus k. Okay, and so here I'm just going to specify how that works when we have basically k is equal to 2 and we are in n is equal to 3. So it means we are able to return a 1 form, which basically is a vector, from a 2 form. So we are going to have, for example, I'm just listing out, I'm not too sure where, let's actually do it here. So if we've got k is equal to 2, n is equal to 3, and you need to specify in principle that we are using the Euclidean metric. Then we have the following, so dx dy, the wedge of dx dy is equal to dz. Then we've got that the wedge of dz dx is equal to dy, and then we have that the wedge of dy dz is equal to dx. And so this is something we've seen in a previous video, so I'm going to put the link to that video here if you want to see how that works. But the bottom line, therefore, is that if I look at star omega, this is going to be omega tilde xy dz plus omega tilde zx dy plus omega tilde yz and then dx. Okay, so because I actually write these things with dz, dy, and dx, I can try to use notations that we would be traditionally used, for example, when we look at one forms, when we look at vectors. And so what that means that I could try to express this as omega x dx plus omega y dy, sorry. plus omega z dz. And so what that tells us is that we can write the following. Omega tilde xy is equal to omega z. Omega tilde zx is equal to omega y. And omega tilde yz is equal to omega x. Okay? Now, the reason why this is interesting to make this connection with the Hodge dual is because it's twofold. The first thing is that the Hodge dual of omega is basically a line integral. So the differential element of a line integral, so you can view that as, so for example, in that case, we are going to have that, physically speaking, if you will, the Hodge dual of omega can be written as some sort of vector omega and then dot dl, as if it were essentially the dot product between a vector field omega and then a line element dl along some curve. Okay, so that's what we can do in terms of interpretation. Now, because I've defined a sort of field that is a vector field with simply three components, omega x, omega y, and omega z, then I can actually try to express what omega itself corresponds to. So this connects to that in terms of interpretation. Okay, but then I actually can write the same thing here. So the form omega, so Hodge dual, and then the form omega itself is basically going to be omega z dx dy plus omega y dz dx, and then plus omega x, and then dy dz. And as it turns out, you can interpret this part here as being the flux, so the differential component or part of a flux, of the flux of the field omega. And so actually here, this is going to be the flux ds, and where ds here is basically the surface element on some surface that you would have defined. So here you need to define a curve, here you need to define a surface, and the way you're going in general to define that surface is basically by taking these pairs. So you're going to create some parallelograms, elementary parallelograms, and then you give a direction to that parallelogram which is normal to these dx and dy, for example. And in fact, this normality aspect of characterizing parallelograms is justified by the Hodge dual. Okay, so all of that kind of comes together. Traditionally, you would use the cross product, but in a previous video, which is the same as where we saw this, um, uh, uh, maybe not the same actually, but in a previous video, we've seen that actually the cross product comes from the Hodge dual, okay, in exterior algebra in general. So basically that's what we have. So here I've got the flux, and that's what I want to do. So the bottom line is that I can write that if I write on any arbitrary domain in R3 that is here, that has to be two-dimensional, okay, because I'm using a two-dimensional form, like a two form. Then I've got that this is omega.ds, so that's the flux of omega across the boundary of omega. And this I'm going to say, well, this is basically the integral of omega. And then again, under the condition that omega z, omega y, and omega x are all well defined, no divergence anywhere in these particular areas, and the d omega likewise within omega itself, then I can write that this has to be equal to d omega, and then over the entirety of omega. So what does that mean here? Let's actually work this out. So d omega d omega is going to be just this quantity here. So that's going to be, let me put it, yeah, so we are going to have d omega z, and then wedge dx dy, and then plus d omega y, and then wedge dz dx, and then plus d omega x, and then wedge dy dz. Okay, so I hope you can see. Yes, so that's the last one. And so then what's going to happen is that I'm going to expand here the d omega in terms of total differentials. So this d omega z here is going to be the total differential of the function omega z. Okay, but you need to remember that this total differential is going to involve dx, dy, and dz. But then what you need to remember as well is what we've seen here. If I have dx wedge dx, this is 0. dy wedge dy, this is 0. So for example here, the only non-zero contribution is going to come from d omega z dz, dz, and then wedge dx wedge dy. Okay, if I had anything else, I would obtain strictly 0. Okay, so the bottom line here is that I'm going to obtain the following. This is the integral over omega, and then I've got d omega z dz dz dx dy, then plus d omega y dy dy dz dx, and then plus d omega x dx, and then dx dy dz. Okay, and as it turns out, basically I'm just going to, I forgot, by the way, this is here I need to integrate. Okay, so that's what we have. And so what I'm going to do, and then I'm going to simply erase and write basically what this is. But first of all, we need to swap these things to obtain the volume element here, the so-called volume form dx dy dz. So I need to swap things. So for example, here, I actually want to bring the z, the dz, toward the end. So I do a first permutation with dx, because dx needs to be brought forth at the very beginning. And then I swap again dz with dy. Okay, so I'm accumulating basically a minus sign and a minus sign. So minus times minus is plus, so no change of sign. And then likewise here, I need to swap dz with dx first. So here this is 1 and here this is 2. While here I want to do that first. So 1, I have a minus sign, and then 2, I've got another minus sign. Okay, so basically that's kind of what I get. And at the end of the day, and I'm going to write the result here. So just erase 2 seconds here. And so I can put that all together, and I'm basically going to get, you probably notice that if I factorize by this volume form, I'm getting that this is the divergence of the vector field omega over omega, and then dv, where dv is the volume form. Okay, and so this is the divergence theorem. And you see that this is very general. I've used here, of course, you need to use some kind of coordinates, but in principle, that would work whatever coordinate system you decide to take. And that's going kind of to work. Okay. So basically, that's it. So in the next video, we are going to see how the Stokes theorem can be retrieved in the very same fashion. But basically, that's it. And again, we are going to see later on some applications of these things in fluid dynamics. Okay, so if you've got any comments or questions, by all means, do let me know in the comment section. And otherwise, see you in the next video.